Oh, thank you. I meant to fix that earlier. I saw it. All right, mis estudiantes, this is a great review of isotopes, right? It's thorough. The one on the back has ions on it, but I'm gonna do ions later with you. So just a quick review. So tell me, number 1, 2, 3, 4, 5, 6, 7. Which row do I need to do first? Because that's not the one, because you were like a little confused on it. Start with 1.
Oh no, okay.
Which one do I need to do first? Yeah. 6. Okay, so lead. We know lead symbol is PB. So I want to go ahead and put PB right here under the isotope as its label. And then you guys have to tell me what columns. Oh, there we go. Okay. So PB, and I know for the atomic A to Z notation, I also have to put PB here. So go ahead and find lead with its atomic number. 82. Okay, so 82 is its atomic number, so you have to write that down. Oops, I'm putting it on the wrong row. So it's the Z number is 82. That's the number of what as well? Protons. So its atomic number is 82, and its number of protons are 82. And if it were neutral, electrons would also be 82, right? But you can see we got 82 and 78. So I can go ahead and tell you this is an ion because I don't have equal protons and electrons, correct? So can you tell me what the charge is at this point in time? Maddie, tell me what the charge is at this point in time. All right, so will you do me a favor? Focus with me. So this is 82, right? This is 78. If I were 82 and 82, it would be neutral. But I've lost, what? 4 electrons. If I lost 4 electrons, what's my overall charge? Positive 4, because I have essentially more protons. So that's going to be positive 4. And I'm going to put that just right here where it says A to Z notation, because I'm really making a complete picture of the charge, the protons, the mass number, and the symbol. Yeah.
But you also put it on isotope because for oxygen they also.
Yep. So you could also put it. I have it under A to Z notation right now. I'll just squeeze it over here with the isotope, like the ion is indicated above it with oxygen. But overall, we just consider protons and electrons and find that. Okay, back to the start. 214. What is this mass number? Where else does this go? Okay, under the isotope. I'm running out of space here, but this is 214 as the top number. It's also the mass number, which is called the A number, 214. So we've got like 3 ways to say literally almost every single subatomic particle. But so this entire box right here says 214 over 82, PB, and then 4 plus. That's the A to Z notation. And this box right here has 214, 4 plus, and PB in it. Yeah.
You know how in our table it says for lead it's 207?
So that's its average atomic mass, right? But remember, average atomic mass came from all the isotopes being considered together in their relative abundances, and we're like, okay, we averaged it, it's 207. That's just saying this particular isotope is heavy, it's super heavy. It's 214, not 207 or 208, whatever it says. So 214 being its atomic mass, being its mass number, is just a particular isotope. Its atomic mass is what, 20.20, okay? That's atomic mass units, right? So 207, that's just an average, not a true isotope, that's just an average. And then how would I get neutrons? What would I be doing? So, right, the mass number, 214, minus the proton number is 82. What's that? 132 neutrons. You are going to have to do the mass itself, that's the actual isotope, minus the protons. Don't do the average, because that's not the isotope of interest. That's not the isotope we're talking about in this one. Yeah?
Is it okay if some of the atomic mass is the same mass number?
Yeah, because that means we selected the isotope that was the most abundant one, because that most abundant one always controls the atomic mass to be really close to itself. Okay, so I did number 6. Is there another one I can do right now for you guys? Yeah.
Number 5.
5. Okay, so right above it, I'm gonna squeeze that in there. Okay, so we got oxygen, right? Maybe I can just write that down here. Let's just write this a little lower. So this is O2 minus 16, and then for the isotope A to Z notation, what would you guys be putting? I know 16 here. What else? 8 as its atomic number, and the 2 minus still exists. That's like the complete picture. So where else does 16 go? Let's see, what? Is that the mass number? Is this the mass number column? Yeah. So 16 is the mass number. Where else does 8 go? Proton number, which is, I think, this column. Yes? Now, let's go ahead and consider, since we're talking about protons, let's go ahead and look at electrons. Normally, they would be equal, right? But in this case, what do I have? More electrons. I've got 2 more electrons because of that charge being a 2 negative. So being 8 for protons, what would it be for electrons? 10, okay? And then 16 is its mass number. 8 is its proton number. Subtract those and you get neutrons. 8 there for neutrons. And then what's its average atomic mass for oxygen? It might be like 15.999 on some of your periodic tables, or it might be 16.00. It really does depend on which periodic table you got presented with your information. And then I think the only other column is this one, which is its mass. What is that one? Atomic number is 8. Okay. Yeah. It doesn't matter. Yeah, it doesn't matter. Yeah.
You actually do row number 1.
Go back to row number 1. I can actually use a chart because I can't see what's going on here. Okay, so A to Z notation, Rn. What's its mass number? 222. What's its atomic number? 86. And then 86 also goes where? Atomic number here. 86 also goes where? Proton number. And it happens to be neutral if you see no charge. So your electrons are also 86. Okay? So where else does this mass number go? 222? Mass number. And then where do you find the atomic mass? Periodic table, what's the average? 222.018 AMUs. Okay? And then how would I get neutrons? 222 minus 86. What is it? 136. Thank you for doing that math. Okay, I'm going to stop there for now. I feel like I've done enough of those for us. I want to take just a couple questions on problem set 5. So let's look at some consistency here, because we've had this for a number of days, and I don't want to spend too much more time here, because then we're not going to be respecting everyone's time equally. So I'm going to take a couple questions. You guys might have to read it to me. I will pull up my work as well. Or my, yeah, I'll pull up my work as well. Go ahead, Caroline, what question?
Number 10.
Number 10, okay. I'm just going to pull up.
Of the problem.
Number 10 of the problems, I got you. Do I have my answer key? It's hard to tell. 1 second. I'm going to try to actually put the entire answer key on the board so I can show you guys at once. So now the computer's frozen. Give me a second. So number 10 had the angstroms association on the spectroscope first. Number 10 said, what was the number in the spectroscope reading? 3.50. So 3.50 in the spectroscope is actually how many angstroms? 3,500, right. Okay, here we go. I'm in business now, people. I'm in business. Here we go. Number 10. All right, so 3.5 in the spectroscope is actually 1,000 times greater, so 3,500 angstroms. And then what you guys probably did in your paper was convert from angstroms to meters by using 1 times 10 to the either negative 10 meters is equal to 1 angstrom. So 1 times 10 to the negative 10th meters is equal to 1 angstrom, or vice versa, 1 times 10 to the 10th angstrom is equal to 1 meter. So throughout that, though, you should just be getting the wavelength of 3.5 times 10 to the negative 7th meters. That is your wavelength. From there, you then had to find frequency by using the speed of light formula. C is equal to lambda times frequency, dividing by lambda, or the wavelength in this case. Here's my work with units in all. 3.8 or 3.00 times 10 to the 8th meters per second, and then divided by 3.5 times 10 to the negative 7th. Your calculator will not know what's in your denominator, guys, unless you're very, very specific. So you've got to put parentheses around your numerator, divided by parentheses around your denominator. It will not understand that those multiplied times 10 things go with the numerator, go with the denominator. So it makes sense for 8 minus a negative 7 that the exponent goes up to 14. That makes sense. So 8.57 times 10 to the 14th per second is our frequency, or you can call it hertz. I'm going to stick with per second for the time being, because as you find your frequency, then you then have to plug that directly into your energy equation. Is that, what's up?
What is the exponent on the 3.5
Times 10 to the negative 7. Good. Thanks for trying to check that with me and make sure your calculator, we're reading the same thing here. I do have butterfingers sometimes, but we all do, right? Okay. So you have your energy equation, which is E is equal to hv. You take your frequency, you plug it into your V, and your h value is your Planck's constant value, 6.626 times 10 to the negative 34th, and that's joules times seconds. You'll take the joules times seconds, relate it to the per second, realize that seconds and seconds can cancel, leaving you only with joules. Okay, so I'm gonna leave that there for a second, Julian. There would be 1, 2, 3. 1, 2, 3. Yeah. So what is this? 5? Is it 570, 57, 568? Okay. And I may have written it correctly on my answer key. Sometimes I need to. I just don't do it on my work. 1 second. Thank you. Mercy.
Just so I really small, like the number 1 in the answers, I got positive to the 11th, and in the answer sheet says 2 negatives.
So I also go positive to 11. There's a, well, I told you guys I was going to be uploading the actual answer key that matches the actual answer key. When I was doing subscripts and superscripts, when I'm doing positive and negatives on the very one that you printed out on your problem set, I haven't updated that in years. I'm so sorry. But you have a picture on your documents page, and it says PS5 answers, and this is it. So that's your answer number 1, right? So don't doubt yourselves. You are probably doing it right. If it's an exponent that's a negative positive, check with this too. All right, good question. I have uploaded this on the website. Another question from PS before we move. Yeah, Chloe. Very last question under the chart. Do you have that question? My computer's frozen again.
It's like outer energy associated with transitions between higher energy levels and those that are between lower energy levels.
Okay, so if you were, it won't move. Okay, there we go. If you were considering all, and you can barely see this is a very, very bottom of the board. Okay, I'm sorry. If you were considering like the 6 to 5 drop, or the 5 to 4 drop, or the 4 to 3 drop, and so forth, that's not a lot of energy. Like their rings, and even if you look on the board model, their rings are pretty close together. But the biggest drop in energy comes between energy level 2 and energy level 1. So I don't have a picture up here, but it's like, let's call that energy level 3, let's call this energy level 2. Energy level 1's way in here. So you've got a big drop from the lower ones versus like a little drop in the upper ones. So that releases a lot more energy, because as you get closer to the nucleus, the electron becomes much, much, much more stable. Yeah.
How do you calculate energy, like, on the table?
From the table, that like last table,
Yeah.
you had to probably look at the frequency I gave you. So like, do you have a specific example?
No, it's just like every single time I was trying to calculate energy, I got it wrong.
So, well, here's one example here. Let's calculate frequency. So like, for example, the very first one gave you 6 to 5 as the drop, and they gave you frequency as the only given information in the table. So you had to take your frequency first, and I just went ahead and calculated wavelength, but frequency is that great variable because you can go in either equation. You can find both things immediately from frequency. So I took my frequency, I utilized that to find the wavelength, so that's our speed of light equation here. Again, meters per second over seconds, or per second and per second cancels, giving us meters. So that's just the wavelength. I think you said you're good with that. But the frequency also is useful in the energy equation, E is equal to hv. So when you take that, 10 to 13 per second, and you plug it in over here with your Planck's constant, 6.626 times 10 to the negative 34 joule seconds, the seconds and the per seconds cancel, leaving you with the negative 34th plus 13th. The exponent drops quite a bit to negative 20th. So plugging that in appropriately is about the only thing. Say again?
That's 2.66 and 2.56.
This right here is 2.66.
Okay.
Okay, one more question. Yeah. Not the table?
Yeah. Answer those, the bracket, and
The electron configuration. Justin, what's up? Okay, give me a second. You might have to make your own solution then. Make your own solution. So we're talking about ions, right? Oh, you could, yes, you could put just the brackets of the noble gas. That's really cheap, so you can do that. That's fine. But I want you to be able to be comfortable recognizing if you had the full out electron configuration, where are those electrons being gained or lost? And we all know they do end up in the electron configuration of the noble gas.
So if it doesn't, you have to use noble gas in that.
Yeah, you shall not put anything else in the noble gas shortcut except for noble gas.
Okay.
Yeah.
And you can only go forward.
Yes, you cannot go backwards. You can take this noble gas and subtract 3 electrons. It doesn't work that way. It's a building. It's a cumulative electron building. Yeah. 6, this one. So I told you, and this is only one example of an excited state. This is one example. Yesterday I told you guys could put it in a higher energy level itself, but technically we all know that if we're going from 4s, which it was 4s2, right, for calcium, we just need to go in and then sequential next direction, so next energy level. You could put it up in 5s. You could put 1 in 5s, or both of them in 5s. 3p is actually a little bit higher in energy than 4s, and I'll remind you of that with the off-ball diagram. That's not it at all. There's AP. Okay, so I'll remind you with the off-ball diagram what that looks like. So I showed you one time. Oh, there it is. Just missed it. I see your hand, Caroline. Wait a second. So this is the 1s, 2s, 2p, 3s, 3p, 4s. Oh, I went down to 3p. That's your question. You could go to 3d or 4p or 5s. You can go to anything higher as an excited state. Okay, Caroline?
Scroll for number 5.
Be specific. Are we talking about the
In all the
energy or the
electron configuration.
electron configurations? All right, and this is going to be my last question for just right now, guys, because we need to kind of get off this topic for a little while so that everyone gets a break from it. If I can find, there it is. 5. Oh, sorry, electron configurations. Oh, but the particle wave duality one. I don't remember how it was phrased. Relate the particle wave duality to
It was photoelectric effect to
quantum mechanical model. Okay.
something.
So I'll just read, right now I'm just going to read off my answer for you and I can further explain. Particle wave duality, which is what the question was regarding quantum theory. Is that right? That is number 5. Yeah. Particle wave duality of nature. At high speeds, energy and mass will convert over to each other into light. So basically talking about how we could shine a high energy photon or light onto that metal. Do you remember we draw that piece on the board? With like a piece of potassium metal, we drew the light, hit the metal, and it popped an electron out. Well, the reason it can do that is because these electrons live in these funky shaped orbitals that are farther and farther and farther away from the nucleus. So that encompasses the quantum mechanical model's orbital theory versus Bohr's orbit theory. And so these electrons have energy, and then once you shine the light on them, you can bounce them to a higher energy level and even out of the actual full orbital if there's enough energy to displace the electron. So pull that into one sentence.
So the light can
Excite electrons and
electrons which
can maybe even displace the electron out of the element entirely. Sometimes it just jumps to a higher energy level and then it falls back down. There's enough energy, you can pop it out. Okay, halt on problem set 5 for a moment. Okay, do me a favor. Go. Okay, so we're gonna switch to problem set 6 our reading guide 6 relay stuff. What did you read about or write about on your problem set? Your reading guide 6. Periodic table. Okay. What else? Different metals and groups and stuff like that. What else?
The trends.
The trends. Okay. We're gonna figure out more about the trends in a second. Okay. So everyone should have a periodic table card in the front of their on their desk someplace. Go ahead and grab an element. Grab an element. Okay. Everyone's got a different element in front of them. All right. So some of you guys have prettier elements than others. So I'm gonna go ahead and pick one. Let me get one of those stuff for the guy. polonium. Polonium. Okay. So using this, wait for it. Look on the back of your card. All right. So you've got information about its plate, its melting point, its electronegativity, valence, group, periods, group numbers, electron configurations, which they call electron shells, atomic radius, and so forth. Okay, so within your little 4Zs or 5Zs, I want you guys to get up and order yourself in order of atomic radius. Smallest radius to biggest radius. In your small group, yes. Stand up. Order yourself in order of atomic radius. Standing up, standing up. Hold your cards like this so I can see it. I don't know if you have. All right, and everybody look back here at this group. Let's hold your cards out like this so we can see. Look at these guys. Okay, so we got vanadium. I'm not going to point this laser at your face, okay? I'm not that person. There's vanadium, chromium, manganese, iron, and cobalt. Can you, okay, so is this in order from smallest to biggest? Okay, so they're from small to biggest, from cobalt to vanadium. Okay, look on the periodic table. Everybody look on the periodic table. Can you find their elements? Where are they at? Okay, I see you pointing. Are you pointing here? Okay, so the trend for their sequence of elements, do they increase in size from left to right or right to left on the periodic table? So they're increasing from, what are you, cobalt? Yeah, so you're increasing from cobalt to vanadium. So they're increasing from right to left. Okay, let's look at another group. Rishi, let's see you guys. So we got manganese, or magnesium, aluminum, fluorine, and neon. So who's the biggest? You got the biggest element. Okay, so tell me, how is it increasing on periodic table? From left to right or right to left, according to your guys' grouping? So there's neon over here, fluorine, aluminum, aluminum, and magnesium. Right to left, huh? Okay, I wonder, can you guys all verify, how is your atomic radius increasing? Look at your order and look at your table. So yours is increasing now? Yours is top to bottom? Okay, wait for it. I'm going to get you in a second. Do I have anybody else that's increasing, not right to left? Okay, so Nick, go ahead and tell me else. So let me see. We got helium. What else? Helium, hydrogen, beryllium, and lithium. Okay, so helium, hydrogen, lithium, and beryllium. Okay, so they have a little weird quad group, right? All right, I need all the noble gases to find each other. Go ahead. If you have a noble gas, then I'm going to say go to Nick's corner. If you have a group 1 or group 2 metal, go to Rishi's corner. That corner over there. If you have anything else, come over here. I don't know. Noble gases that way. Group 1 metals over here. Everything else over here. All right, and I got the cool kids over here. Cool kids down here. So noble gases. Hold up. Let me see your order. Get in order. Get in order of atomic radius. Your hydrogen. You're not noble gas. Go that way. Go that way. All right, guys. Eyes on the noble gases. Noble gases. Okay, so they have the order. Who's the biggest? So helium, no, so argon's the biggest, neon's the second biggest, and you're the smallest. Okay. Look on the periodic table. Find helium, helium, neon, and argon. So they're increasing. Who's the biggest?
Argon.
Argon's the biggest. Okay, so how is it increasing? From top to bottom or bottom to top? Bottom to top. Okay, so go back to your seats. Go back to your seats. Hold on to your card. And I'm going to tell you one thing before you have to grab your laptops in a second, okay? Oh, gosh. And on your periodic table that you have colored with your SPDF stuff, can you pull that out for me? Periodic table that you colored with your SPDF, your electron configurations we did the other morning for wormhole. Or it can be the other one. The other one's really crowded, though. It already has a lot of information on it. So, here we go. You are going to draw So you got this little periodic table. It's kind of a periodic table. All right, you're going to draw an arrow. The way we said the trend for atomic radius was increasing or decreasing. So down the groups, was it increasing, or down the groups, was it decreasing? So who was bigger, helium or argon? So my argon, so those three people really know because they were the elements. But so going down, so draw an arrow down the groups. What property were we looking at? Radius. Okay, so the atomic radius is increasing. So I'm just labeling what my arrow means. Atomic radius is increasing down these groups. Atomic radius is increasing down these groups. So I'm just giving myself some help here. All right, so going back to, I think, my transition metal group, I think Jillian and Carson and somebody else was in that group. The whole group, right? You guys had yours across the row. What was happening to your radius? Did it increase right to left or left to right? It increased right to left. And I think we have numbers of people who did that as well. Okay, so this is another trend. Same atomic radius trend, but now we're talking across a period. So it increases from right to left. Oops, I just moved the whole thing. Okay. It increases, so this is again atomic radius. It increases, it's increasing from right to left. Okay, so I've got you started on how to remember how the periodic trends trend. How do they work? How do you read them? So what you guys are going to do is you're going to explore this a little bit more. You're also going to explore a little bit more about the properties of metals, nonmetals, and metallics. So you did some of that investigation on your reading guide 6. So how much of that was new for you? Like the properties of metals and nonmetals? How much was new? Most of it? See, I always think that people learn that in middle school, and I think some people do. It depends on where you went. It depends on the level of detail. I have a horrible memory, so I can't remember middle school if I wanted to. Just the like, weird boyfriend kind of stuff, but whatever. So, like, anyway, so more on that later. You guys are going to be working with atomic radius, ionization energy, electron affinity, and electronegativity. Those are the 4 trends of the periodic table. You read about that in your problems reading guide 6, but you're going to do a little bit more interactively. So I'm going to have these 2 tables if you grab your laptops, and I'm going to get the next ones, but I'm going to explain to you on the board what you're doing first. So when you go to this bit.ly address, you'll see, if you have your own laptop, you can pull it out, that's fine. When you go to the bit.ly address, you'll see this. I've got you going part by part. So the first part gives you information about metals and nonmetals, and you can draw something with this, okay? Be a little bit more creative. Just on your reading guide, you only wrote down the specific properties. So I have colored paper, I have markers, and etc. You guys can, even if you want to make a foldable order, half of it's for metals and half it's for nonmetals. You can be creative. Write down some properties of this. You can spend 5 minutes on that, you can spend 15 minutes on that. Depends on what you need to do for yourself. The next 2 things, so my next 2 groups, can you guys go grab your laptops, 2 tables? You can walk through the property tutorial. It's got a really kind of cool way of representing the properties, but I'll leave the first part up to you on the level of detail you need to do. Specifically, part 2 has a periodic table you guys will be working with, and at the top it says properties, and you can see all of these different radio buttons you can click for the properties. Whenever you get there, I give you specific instructions on what I want you to do. So questions to answer, you'll be answering these in groups, that's fine. If you want to write this stuff on your periodic table, that's also fine. If you want to type it up, that's fine. I give you a lot of autonomy on how you're crafting it for yourself. But the only thing is, if you would like to work in groups and you all agree, we are going to type this. You remember how to make a copy of my documents? You can make a copy under file, and you can make a copy for your own group, and you guys can all work on it, but you need to kind of come to that decision together. Part 3 is a periodic table mystery. I'll let you guys read that, and I'll let you read part 4. You guys go get your laptops. So, you're going to start. Your laptop gone right now? Justin, hold on. He doesn't know that he grabs people's laptops. Give me a second. You can get clothes. Here is that bit.ly address. You can also go to my website. And I'll show it's under homework. Momentarily, once you guys can grab your laptops. All right. You're okay. I'll get you there. So since some of you guys know what I'm looking for, you guys can talk in your groups if you're going to be writing this all down individually, or if you're going to be working on a Google Doc together. I do recommend you write down some things for your own study purposes. The capitals do matter, by the way. Your laptop's coming up.
No, it's the same thing do at the end of class.
You'll have parts of them.
And will the rest be homework for the weekend?
I'll make that decision in about 30 minutes. Okay? You'll notice that I really haven't taught you anything today. We just went over homework. So I thought we'd actually get to this about 20 minutes ago. So yes, you guys, you can read the instructions up here. Complete this exploration in your groups. You can make a copy of the Google Doc if you want to, but you need to write some of this down. You want to be on part 1. I know that the reading guide had a lot of information for you, but you also need to write something with that document they created. There's markers and paper for that over there. I am coming around to collect problem set 5. If you need a stapler, I'm bringing it with me.
Did you look at That's definitely I've been doing it crazy. I can really feel it. You don't have it. No, I do.
I'm on the well, I'm on the thing. I don't know if I'm doing
Oh, that's not an L, that's a capital. But the other will teach you. You'll be able to teach them under chapter 1. I don't know how I studied. I thought I did well. I only got like a 70. Study so hard, but wait. So I step one is to write down the properties. So I step is that yeah.
So just to clarify, yes, this is totally fine to be a collaborative effort. Second, under the, let me pull that document back up. So, and I will do this, I'll go ahead and write this down now up here. Something colorful or a foldable or a foldable or a picture, anything that you are writing down for part one is fine. But I'm telling you now, you don't always remember things you type. You generally remember things you write. Some people are good at remembering things they hear. Some things are good at remembering things they see. So I'm trying to get you to represent this in different ways. That's why I'm giving you some flexibility, but some minimum requirements. Minimum requirement, you write down something on your own. You can obviously work together, but write down something on your own that relates to these properties. Walk through the tutorials if you need to, but this won't take you very long. This is on Reading Guide 6, so you have a good background knowledge there. When you get down here, you guys will need to read and actually start documenting some of your collaboration. And this can be on the document or it can be written. And after that, you guys will be reading there. But I'm letting you get started by yourselves first. Give me some highlighter on it. Get some color on it.
It's just like some of the stuff you have to write down. You should just keep it for yourself.
Together, that's all. I just need to have something written for yourself that's exciting. Any questions about part one? You guys will access the bridge, talk to everyone, together much higher. You submit these together. Probably to be typed out. But right now, we're showing part one. Everyone's writing something down for themselves. So how did you That's cool. There is no perfect. There's no like right goal.
I remember it was me like
All right, so if you have a question, you need to raise your hand. But I'm leaving you to communicate in your groups right now.